it's an interesting world. So I'm here, I guess, not to give you the hardware perspective, and not to give you the really sort of quantum technical perspective, but say when you come to this field as from the sort of end user scenario, because really if we imagine that quantum is going to be a big feature in some modern data center and is going to be a sort of integrated part in future computing technologies, that's because we also imagine that there's some real benefit for users, that for a particular problem this hybrid computing solution is just going to deliver something quite profound. So I'm going to give you the perspective of the user, sort of problem-centered, thinking, how on earth am I going to use this? So, and all of the sort of issues that we're grappling with there. So our program, we have a particular focus on the life science application space. You might say, why go all the way to life sciences when there's many other problems? But I think the life science application space is actually really interesting for this. We have aspects where quantum descriptions of biology might be important, but a huge number of the problems in life sciences are actually sort of classical computational problems. There's a lot of big data problems. There's a lot of heavy simulation problems, DNA sequencing, things that are done on a huge scale the world over. So it's actually a really sort of big and diverse space for us to think about problems. So we're in a program, our mission is to enable the development of fault-tolerant quantum computing hardware. So that's the other part of our program that I'm not talking about, but also with this focus on applications and algorithms in the life science space. So we're a full stack program. At some point, the ideas that we develop, we're actually going to have to make it work on this hardware, but we've got some years to do that. We are in what we call our preparation phase at the moment, but we're sort of looking towards a 12-year program, all with the sort of end goal of let's try and do something useful for life science on a quantum computer 10 to 12 years from now. Okay. So we're hoping that this hardware is going to emerge, or useful hardware is going to emerge. And it's true that there are, machines that one can get access to and calculate something today. But the sorts of machines we have, the sorts of algorithms we have, don't really deliver something that we anticipate we're going to do something useful with. We think there has to be a whole lot more development before we anticipate that this will happen. I think we've got a talk later today about error correction, which I think is one of the really key factors for us to start to see something useful from the user case. So I think this, in a sort of classical sense, this is much more what we're dealing with. We're dealing with really, technology in its infancy. And you're also dealing with a whole group of people who've learned to think about computational problems, who've learned to code, not on machines like this. We don't have the sort of training that says how do we solve big compute problems on really sort of primitive hardware. We're used to solving it on modern hardware, and it feels like quite a different skill set. So what do you have to do if you want to solve something, use a problem in physics, chemistry, life science on a quantum computer today? So you have to use technology that you often at the point that you start the project, you don't actually know what the performance specs of the machine are going to be. Some of these machines, the performance specs are going to vary from day to day as well, just to keep your things interesting. You have to develop all the sort of new methods, potentially new algorithms that go along with that. And you have to, as part of that, compensate for the limitations of the technology. There's also a very strong agenda that we should show that there's some advantage to doing this. It's not enough to just do a calculation. We could have done somewhere else. We have to do something kind of remarkable with it. And then if you're coming from the use side of things, there's also a sense of, well, we want to improve our understanding of the world. So that is a different question from just calculate something and just calculate something, maybe speeding things up. and they'd like it now, even though the hardware's not really there, I would say, there for us. So when you come, you might come thinking, I know about chemistry, I'm interested in calculating life science problems. And then when you first interact with people with quantum computing, they'll say to you, okay, well, what's a hard problem in chemistry? And it's a sort of interesting thing in that, because typically what we think of as the hard problem, or what springs to mind when somebody asks you that question, are all the problems where we've made a huge amount of progress with classical computer technology, and we can't, get all the way. But these are the problems that, classical hardware is really good at, which sort of feels like a problematic place to start. And then the next thing they say, well, okay, but what is the Hamiltonian? Because the way that we're going to have to sort of implement this on this computer is not to sort of think in a natural framework about what the problem is and what's going to happen, but is something of quite a sort of unnatural way, because it's really trying to sort of optimize for the hardware as opposed to optimize for the problem. And then if you say, I'm not sure that this is working, then somebody say, well, can't we do catalysis, enzymatic catalysis? What about nitrogenase? And a lot of people will say, well, why is everyone still talking about, why does everyone keep talking about nitrogenase? You can come and hear that quantum computers are going to solve this problem. So the reason that people like talking about nitrogenase is a very famous paper that said, quantum computers, this might do something really interesting for enzymatic catalysis. And it might. But this is the workflow that you have for that sort of problem. And everything out here on the right, in the blue, this is everything you would have happening on the classical hardware running alongside. That little box over there in the orange, that's the part that you have running on the quantum hardware. So speeding up this process is how much of the cost is spent in that little box. But improving our understanding of the process, that limitations, whatever approximations we have in this very small part that the quantum computer can deliver, if that's not the part that's sort of limiting our understanding of the problem, we can speed up this whole process, but still not deliver any improved understanding from a sort of chemical, life science, biology point of view. So this is where you sort of, there's a gap that comes from the user's point of view. And this is the same with all kinds of technology, but I think this is something that's really important to realize, also in the sense of the hype that's coming in this field. Because it's one thing to demonstrate that we can do something, it's another thing to demonstrate that we can do something really useful for humanity with this sort of technology. And there's a way to go to see where we can get to with all of that. I'm going to skip ahead because I think I'm running short on time. But I would say that sort of the first point I say with that is we have to think about the questions we're asking. What questions are we asking from this hardware? What are our expectations? What's sort of realistic? What's the role that this sort of hardware is going to play? I'm going to skip ahead even a little bit further. Oh no, that's okay. I'm sorry. We'll keep going. So the next thing is, you might say, okay, well, where are we going to find all the problems that we're going to do? And if we don't think we have them sort of sitting around, you're not short of resources out there. There's reports by management consultants and other groups. There's scientific articles. People will tell you that quantum computers can do all kinds of things. But when you look into the details in a lot of these publications, the link between, really being sure that we can do something useful with the hardware and the problem itself is quite loose. There's a lot of, hope in there, I would say, between some of these connections. So the other thing I think we have to think at the moment is we're in a state where we have to reconsider what we think of as work. I mean, at the moment when we approach a sort of classical computational problem, we have a sense of the problem, and then we can calculate it. And it's just a matter of, okay, calculate, compute what is useful here. But here, this thing of whether we can even link those two things is part of the work that we have to develop. 3 minutes. Okay. There'll be a million suggestions of different things that you think, oh, what could we do? And there's all kinds of things that would spring to mind to do. And you sort of have a sense of, I'm surprised nobody has thought about this before. But I think everybody has thought about these things before. But I think there's a culture in the field that we talk about problems when we've solved them, not when we've started grappling with them. And I think that would be something that would be really interesting for the field to develop together, is thinking about how do we talk more about the unsolved problems, how do we talk more about the failed cases, how do we communicate our negative results so that we don't have this sort of wasted duplication of effort. The other thing that I think is kind of interesting in a climate like this, where there's a lot of political attention, there's a lot of industrial attention, there's a lot of venture capital money, there's a lot of university people involved, there's a huge number of different people in all kinds of fields we can imagine that are interested in being part of this conversation. And for those people, these sorts of material is not necessarily the useful way to engage with the problem. So we sort of need another way to have a broader conversation in the community as well. So we are thinking about that in terms of sort of a website, and we're doing a lot of work at the moment building up a database that's going to underlie that website to try and provide a tool that different types of users, but all the way from the sort of algorithm side to the sort of end user, could be at a political sort of government level, could be at an education level, could be at an industrial level, can engage with and get things at different kinds of levels. So we want to reduce communication barriers. And we're done?
I think we're done, yeah.
Very good. And then I will leave this as the last photo, which is just what we were saying. We're learning by doing. And there's immense value in that. So thank you.